Welcome. We will continue our discussion on the mechanical properties of ceramic materials. In an earlier lecture, we have introduced the concept of fracture toughness, the critical flaw size or crack size, and also the fracture stress, and that was based on the Griffith's theory, in which the energy, the total internal energy and the surface energy terms have been maximized, and we have found that beyond a particular critical size of the crack propagates on its own. It does not need any further stress to be applied, because the extension of the crack reduces the overall energy of the system. We have considered this kind of situation where a crack is growing or initiated at the edge of the sample, and a normal stress applied, sigma applied, has been applied perpendicular to the crack direction. So, this is certainly one kind of stress, application of stress or orientation of the stress, in which the crack length is perpendicular to the applied stress. However, that is not the only way one can apply stress on the material, particularly in relation to the orientation of the crack. There may be different other orientations possible. In fact, there are three different modes of fracture, where the crack, the direction of the crack and the direction of the application of the stress are different. So, in the first mode is called the opening mode, where which actually we have considered earlier, where this is the application of the applied stress, and it is trying to open up this particular crack. The crack is perpendicular to this surface and also perpendicular to the application of the applied stress. So, this is what we call the opening mode, and or sometimes called mode 1. In the second mode, the application or the direction of the stress is once again perpendicular, but it is in a different direction. So, one side of the sample around the crack is being compressed, the other being expanded or on the tensile load. So, here it is a kind of the crack is moving along the application of the along the application of the stress, applied stress. So, this is what we call a sliding mode, and one can very well distinguish between the orientation of the stress and the crack here and the stress and the crack there. Still, there is a third mode, where the direction of the application of the stress is actually along the crack. So, this is in the right hand direction, this is in the left hand direction, and the crack is propagating away from this surface. So, in fact, the crack is perpendicular to this vertical surface, the stress is also perpendicular to this vertical surface. Only thing on the top side, top end, it is pushed backward, and here is pulled away from the crack. Okay. So, this is called the mode 3 or the tearing mode. So, these are different ways of crack propagation or different orientation of the crack with respect to the applied stress. As you can visualize, this is one of the most easier way to crack propagate whenever the the applied stress is in this direction, then is it easier for the crack to propagate with a much lower stress. So, corresponding to these 3 modes of applied stress, there are 3 modes of fracture which can be defined, and correspondingly 3 different stress intensity factors can also be defined. So, the mode 1, the opening mode, stress intensity factor is K I or K 1, mode 2 this is K 2, and then mode 3 is K 3. So, it is opening mode, sliding mode and the tearing mode. Now, mode 1 corresponds to the tensile load, and the other one are shearing mode. Shearing this is in tensile load and more critical than others, therefore, same will be the item of discussion which follows. That most of the time whenever we discuss about the fracture toughness, it is this kind of fracture mode which will be more concerned with, because that is more critical than the others. Well, having discussed that, let us try to look at the different techniques of measuring the mechanical properties. Of course, fracture toughness is one of the important mechanical properties which we must understand, or we must measure the value of that particular parameter experimentally. We will come to that, how exactly the fracture toughness parameter can be measured for different samples, and what kind of specimen preparation is needed, what kind of different techniques, what kind of different loadings can be considered. But before that, there are many other mechanical property related parameters which also involves mechanical property of ceramic materials, and let us try to define them and try to see how they can be measured experimentally. The very first one is the Vickers indentation hardness. Well, hardness is always a very important parameter so far as the mechanical property is concerned, and it is the most of the time it is the indentation hardness which is measured. So, with the help of an indent, you made a groove there and try to find out what is the size of the groove under what kind of load. So, the Vickers indentation hardness is basically measures the resistance to permanent deformation, okay, because if you are trying to make an indent, it should not be relaxed, or it should be a permanent indent, and therefore, it is a permanent deformation. So, whatever small it is, obviously for compared to ductile material, for brittle material or for ceramics in particular, the permanent deformation is negligible, and therefore, you need larger amount of stress or larger load to make an indent, but some amount of indent can certainly be done. Since ceramic materials are very hard, we always use diamond, and that is the by definition, because indentation always use a diamond indenter, and it is in the form of a square pyramid. And it is done on a polished surface. Polished surface is required because the overall dimension of the indent is very small. So, until unless there is a polished surface, it is difficult to measure the dimension of those indents. Therefore, it is always necessary that the ceramic material must be polished, ground and polished first, and then on that you make the indent. Based on the size of the square indent, hardness parameters is expressed as, I am not going to the details how this particular formula has been derived, but one can find out in different textbooks. The hardness parameter is in a simplified way, it is actually 1.854 into P by D square, where P is the applied load. In fact, as you are possibly aware, that in a Vickers indentation hardness test one can vary the load depending on the hardness, depending on the surface and many other parameters. So, depending on the hardness one can vary the load. So, load is an important parameter to calculate the hardness. So, where H is the Vickers hardness and P is the applied load and D the average length of two diagonals of the indenter. It is a square indent and you have to find out the diameter, two orthogonal diameters in the orthogonal direction and take the average of it. So, that is a very simplified formula for measuring the Vickers indentation hardness. What are the different precautions you have to take during this measurement? There are few listed here. Load must be optimized so that the corners of indent are clearly visible, but no cracks are formed. Okay. It is very important that we should not initiate a crack. So, the load you have to be optimized appropriately, so that you get a appreciable amount of indent, appreciable size of the indent, so that the measurement becomes easy or measurement becomes accurate, but at the same time you have to limit the load, so that indent does, because there is a stress concentration at the corners and that you have to take into account, so that there is no crack initiated at the corners. In fact, crack initiation means it will not give you the right value. Accurate measurements of the diameter of the indent is of crucial importance. If necessary, one can take help of the electron microscope. Normally, optical microscopes are used to measure the diameter or the dimensions of the indent, and it is in the order of microns, certainly less than millimeter. And if very fine indent is there, one can even take help of electron microscope for accurate measurement, because it is d square coming at the d square coming at the denominator, and so any inaccuracy here in the d value will certainly lead to a larger inaccuracy of the measurement of the parameter h. So, accurate measurement of the diameter is also important. Repeated measurements at different locations are necessary for representative hardness value. Sometimes it is very difficult to find a homogeneous sample for many different reasons. So, there may be grain size different, there may be dual phase materials and so on. So, it is necessary that one carries out a large number of fairly representative number of hardness tests or the measurements, so that an average can be taken and a representative value can be reported. So, these are few precautions one has to always take while taking the measurement. Then there is another very important parameter, which is compressive strength. As you will always notice that for ceramic materials we never normally do not report the tensile strength, because in the tensile strength it is quite poor. So, whereas in the compressive load it is much stronger. So, most of the time for ceramics it is the compressive strength which is reported, and the measurement is also quite relatively easy, because for tensile specimens you need a complicated shape of the specimen, and that kind of complicated shapes are difficult to make with hard and strong ceramic materials. So, it is much easier to make compressive measurements in the form of a cylindrical samples, and it also gives a much better representative strength. So, compressive strength is, in addition to Vickers hardness we have discussed, compressive strength is another parameter which is measured or which is reported to provide the mechanical strength of ceramic materials. So, compressive strength is a much higher than the tensile strength, that is always true for any ceramic material. Typically, the ratio is 8:1. So, if the compressive strength is or 1 is the tensile load or tensile strength, compressive strength is nearly 8 times that of the tensile load. In fact, here is a stress strain diagram. Sorry, it is this is strain and this is stress, which has not been mentioned here, but this is a normal curve of stress strain diagram, and you can see this is the initial elastic range. This is the compressive stress and this is the tensile stress. Okay. So, the tensile load, it fractures here, but if you are having applied a compressive load, it can go up to a much higher level without fracture. So, the fracture or the deformation starts here in the compressive load. In the tensile load, it just goes up to that and fractures. So, failure under compression is more gradual than in tension, and that is also demonstrated here. If you have a tensile load, it follows this line because of the elastic modulus or elastic deformation, and then suddenly fractures, whereas that is why it is not shown here. Whereas in compressive load, you have a more gradual breakdown or a deformation before it actually fails somewhere there. However, as you can see, compared to a normal ductile material fracture or ductile fracture, the permanent deformation or the plastic deformation here is not a smooth curve. It is not a smooth curve, it goes through a lot of serrations. So, it appears or it represents that the fractures takes place in different kind of steps. It is not a very smooth regular progression. Young's modulus is same, more or less same in both in tension and compression. The same line follows so far as the elastic zone is concerned. So, because the Young's modulus is basically the slope of this line. So, you have more or less the same slope. Crack develops vertically during compression, and serrations during compression is associated with spalling of the test piece. Now, this is little bit discussed already, that you have a serrations, it is a more gradual mechanical permanent deformation, but it is not a smooth curve, there are serrations there. And the other thing is cracks normally formed vertically. Okay. In a metallic material, normally the crack appears at 45-degree angle, that is the normal way, normal range of shear stress, normal orientation of the shear stress. However, in a compressive test for ceramics, the crack appear like this, okay. And finally, it combines, the cracks join, a crack can be generated or nucleated at different sites, and these vertical cracks finally joins, and there may be what we call the spalling. Spalling means a part of the sample just comes out of the surface. So, towards the end of this experiment, you will see some of the portions of the surface material just comes out, gets loosened because of the cracks gets joined together, larger cracks appear and they come out on the surface. Okay. So, that is the what we call spalling. So, this is some kind of features of the compressive test which is carried out on ceramic materials. Well, these are another little microscopic aspects of fracture, both in tensile load. This part is on tensile load, this is on compressive load, and we have earlier seen that it is the cracks, or in fact the pre-existing cracks, which are primarily responsible for the fracture of, or the brittle fracture of ceramic materials. Now, these pre-existing cracks can generate because of various reasons, primarily during its preparation, because of the thermal history, and sometimes there will be some kind of a dual phase material having different thermal expansion coefficients, or generally ceramics are thermally or less thermally conductive. So, temperature uniformity is a problem in all ceramic preparations, and ceramics always require high temperature for their sintering and other fabrication processes. So, during cooling, if it is not an equilibrium cooling, there will be always thermal stress generated in the sample, and those thermal stress may lead to different kind of cracks. These cracks are pre-existing in most of the samples. So, that is one of the considerations, or one of the theories of Griffith, that in brittle solids, in brittle material, particularly in ceramics, because of the thermal history, because of the thermal low thermal conductivity, you will always have thermal gradient, and that thermal gradient may lead to local stress generation, thermal stress, and that thermal stress will finally cause some minor cracks. Okay. Now, these minor cracks, or different size of cracks, may not be very critical, as you have seen in the Griffith's theory, that only if the size of these cracks are larger than the so called critical crack length, then that is very dangerous. Okay. If it is the crack lengths are smaller, or smaller than the critical crack length, then they are not dangerous, they will not grow, they will remain there, only they can grow after a very high large application of, or the application of large external stress. So, cracks do exist in ceramic materials, brittle materials, either on the mostly on the surface, but maybe inside the material also. So, in any material you have a different kind of cracks available in a random fashion. Their orientations are quite different, random in nature. So, that is what it is shown there, already there are cracks, and if you are doing tensile load, or applying tensile load, some of these cracks will be more effective or more prone to a propagation, others may not be that effective so far as the propagation is concerned. And that is what this is a crack which is a kind of mode 1 fracture. Okay. You are applying tensile load in this case, in this direction, and it is trying to open up, whereas this is in a slightly different direction. So, the effectiveness of this stress so far as the crack propagation is concerned is not so much. So, they prefer, or the properly oriented cracks will certainly open up, and that is what it says. This crack propagates unstably. Unstably means the sense it is almost an instantaneous crack growth. So, these are very crucial and very critical, and if such cracks are there in large numbers, the material will immediately fail. Okay. It is a very a material of very low strength, particularly under tensile. So, this is what will happen after some time, this crack will suddenly fracture the material. Okay. Now, however, the other cracks which are oriented in a slightly different manner, they may not be that dangerous, and they may not lead to failures. So, this is in tensile, and this is in compression under compressive loads. These are the cracks. Obviously, this crack which is perpendicular to the load will not propagate under compression. The cracks which are slightly inclined or vertical in direction. These are the cracks, all these cracks will certainly extend or propagate or getting elongated under the application of the compressive load, and that is what has happened in the second stage or the final stage. These vertical cracks, there will be some generation of the vertical cracks here. These vertical cracks will finally join with these cracks, existing cracks, and finally they will be spalling. If they are very close to the surface, then there will be release of some portion of the surfaces solid material from the surface, and that is what we call spalling, which we have discussed earlier. So, these cracks propagate stably. Now, this unstably and stably, these two terms must be noted. Unstably means it suddenly fails or it suddenly propagates. Stably means it is a more gradual change, more gradual propagation of the crack. So, under compression it will in both the cases they will be propagate, but one unstably means they will propagate very fast, and where here it is in a more gradual manner. So, that is why you got a serrations here, right. In tensile load it will be sudden fracture, whereas in compressive load there will be gradual fracture or gradual deformation and finally fracture. So, this is what happens under tensile and compressive loads, and compressive load is more common to measure or to report than the tensile load. In addition to that kind of a compressive measurement, a compressive load measurement, compressive strength measurement, you have another very important technique or a type of parameter which you measure is called flexural strength. Flexural strength is of course very common in brittle solids. It is not so important in ductile material. So, metals and alloys do not perform this kind of test so much. They perform in so far as metals and alloys concerned, metallurgist will perform tensile load, whereas in ceramics, ceramist will perform flexural strength or compressive strength. Now, these are two varieties or two different modes of flexural strength. One is called is basically a bending test. You have a support here on the bottom, two different supports, and on the top at the middle of the two supports you have a compressive load. So, it is this force is acting upwards, this force is also acting upwards, and this force is acting downwards. So, there is of course there are standard dimensions for each of these measurements. We are not going to the details of that. So, not any particular gauge length is useful, or it can be measured, you can always get a value, but if you want to standardize this process, there are some standard gauge lengths and standard parameters, standard length parameters, distance between the two probes, two supports, then the width as well as the height. All these things are standard specimens have to be used. But there is another mode of using the experiment or carrying out this experiment. It is called 4-point bend test or 4-point flexural measurement. So, instead of one load point here, loading point at the middle of these two supports, but we have two different loading points. So, it is p by 2, p by 2, p by 2, p by 2, and once again there are specific distances. Here as you can see, this is L by 2. If this total distance is L, this becomes L by 2 between these two loading points, and here it is L by 4 and N by 4. So, that is also quite standard. One has to follow this kind of a standard so far as the loading pattern and the loading points are concerned. Now, by doing this, as you can see in the bottom we have a tensile load, and on the top there is a compressive load. So, this actually gives you some kind of a combination of the tensile fracture and the compressive fracture. So, compared to the earlier one, either you have a tensile load, what we have done earlier, either you have a tensile load or a compressive load. Here both compressive and tensile loads are applicable or applied simultaneously, but by a different kind of mechanism. So, it is by bending tests or flexural test. In kind of 3-point bend test, you have this expression, the sigma fracture is equal to 3 P L by 2 B D square. P is again this load which you have shown here. L is the length or gauge length, L is the gauge length, P is the load at fracture, then it becomes the fracture stress. Okay. So, fracture sigma f is known as the modulus of rupture or MOR, the fracture stress is known as the modulus of rupture, and that is a very important parameter for most of the ceramic material whenever you are interested in mechanical property of ceramics. So, sigma MOR or modulus MOR is very common, so that the mechanical property evaluation is concerned. Whether it can be done at room temperature or it can be done also at a elevated temperature, particularly for refractory you need what we call hot MOR. So, there is a standard test again which is carried out at a higher temperature, maybe at 1400 degrees centigrade depending on the application range or the service temperature of refractories. So, hot MOR is a very important parameter for refractories, but for many others which are used primarily at room temperature, the room temperature MOR is an important parameter. So, once again from this two expressions, one is 3 P L by 2 B D square, here it is 3 P L by 4 B D square, that is the expression. Okay. And P is the load at fracture, L is the gauge length, the distance between these two supports, B is the width of the specimen which is not seen here, and D is the thickness. Okay. So, these three parameters, length, breadth and distance thickness, provides you this MOR. So, that is flexure strength. Now, elastic modulus, of course, elastic modulus, the best way to find out the elastic modulus as per definition, either you make a carry of a tensile load or a compressive load, and then from the stress strain diagram, from the slope of the stress strain diagram in the elastic range, you can always find out the elastic modulus. However, there is for ceramics there are much better slightly different way of measuring the elastic modulus, okay, which is not exactly the mechanical test, but it is a different test. The most convenient way to measure this property is based on the natural frequency of vibration of a rectangular sample when the same is struck by a steel rod. Okay. It is a kind of tuning fork kind of experiment, where if you strike this ceramic with some other material, that means you generate a sudden stress on the material, then it actually starts vibrating, okay, and that vibration has a particular frequency. So, that frequency is related to the Young's modulus of the material which is generating that frequency. So, that is the principle by which the Young's modulus of most of the ceramic materials are used, not by carrying out the normal stress, normal tensile stress or compressive stress. That also provides you, particularly the compressive load also provides you some Young's modulus, but this is a non-destructive way Okay. That was a destructive way where the samples are broken. You have to break the samples, and whereas here you do not really break the samples. So, it is a non-destructive way of measuring the Young's modulus of ceramic samples. So, that is what is, once again to repeat, the most convenient way to measure this property is based on the natural frequency of vibration of a rectangular sample when the same is struck by a steel rod. The formula used for the purpose is like this. The Young's modulus is once again, these are some of the slightly empirical formulas, of course, analyzed by some mathematical means. So, ultimately, of course, without going to the details of that, the formula is 0.9465 m ff square by 2 square by b and L cube by T cube, and then there is an expression 1 plus 6.858 T by L. These are the parameters, these are the notations used in this formula. Young's modulus, E is of course the Young's modulus, m is the overall mass of the bar which you have used, because the total mass has a very important implications of the frequency of vibration. Ff, the natural frequency of vibration in the flexural mode, b is the width, T is the thickness, L is the length. So, once you know the mass, that means the weight of the sample also have to measure in addition to its thickness, the width as well as length, and then you have to measure the frequency, natural frequency of vibration. In fact, there is a computer program which actually automatically measures it. So, it measures, it detects the vibration. Of course, there will be some damping effect also. So, it actually measures the vibration over a period of time and then finds out the natural frequency of vibration and finally provides you this Young's modulus. So, it is mathematical it is little complex to otherwise measure it, but there are equipment available and the softwares are also available which can directly provide you this number, the Young's modulus. Now, then there is also another thing one can measure, the Poisson's ratio by a slightly different technique. Okay. And in fact, that technique again is based on the propagation of ultrasonic sound through the material. Okay. The material, different materials depending on its elastic moduli, the Poisson's ratio and density, it has a different velocity. I mean, it propagates the ultrasonic sounds at different speeds or different velocities. So, and that is directly related to, or that is somehow related to the Young's modulus and other mechanical properties. So, in this technique both elastic moduli and Poisson's ratio may be measured by an ultrasonic method, normally at a resonant frequency of 10 megahertz, for which the formula used are like this. In fact, what we have earlier seen in this course, there are piezoelectric transducers which can generate ultrasonic sounds or ultrasonic waves. So, such kind of piezoelectric wave generators, ultrasonic generators can be used to measure, either generate the sound or get an echo of that sound on the other end, and therefore, by measuring this kind of piezoelectric sensors and generators, you can find out what is the velocity of propagation, and from that you can find out the Young's modulus and the Poisson's ratio utilizing this kind of formula, where E equal to 1 plus nu 1 minus 2 nu by 1 nu rho C L, and this is again another equation for nu So, first of all find out what is the nu, and then this value can be put here to find out the Young's modulus. What are the different parameters here? The rho of course is the density, Cl is the velocity of the longitudinal wave. Here you can see Cl, Cs, and there is another parameter. Okay. So, these are all velocities, different kind of velocities. I think this should be not L, not 1, I think it should be L. Okay. This there is a mistake over there, this should be L, Cl by Cs, and this is also Cl by Cs. Okay. So, Cl, the velocity of the longitudinal wave in meter per second, and this is Cs, velocity of CR wave in once again in meters per second. So, from that you can find out the Poisson's ratio, and once the Poisson's ratio is measured, then you can also find out the Young's modulus, and rho being the density here, okay, in gram per cc. So, this is another way you can find out the Young's modulus. In both the cases actually you have to either you create a sound wave or an ultrasound wave. Well, having discussed that, what are the different properties and how to measure those properties, mechanical properties. Next item we want to discuss how to measure the fracture toughness. Okay. How to measure the fracture toughness of different ceramic materials. We have known that the general condition of the fracture is this sigma fracture root over pi c must be equal to k I c. That is the parameter the fracture toughness. Okay. So, the fracture toughness, if this value becomes more than the actual fracture toughness of the material, then the fracture will take place. Okay. Where y, we have seen it earlier, is a dimensionless constant close to unity depending on the shape of the sample, geometry of the crack, its size relative to the sample size, etc. And ideally the size of the crack should be of the order of atomic dimensions, okay. Which is always not true, sometimes there will be larger cracks also. In absence of which different types of cracks are intentionally created in the samples before they are bend tested by application of external load. So, as you have seen earlier that we have made our calculation assuming that the curvature of the crack tip is of the order of the atomic dimension. However, a crack of the atomic dimension is almost impossible to be created. So, what is done, a crack is created, intentionally crack is created on the sample, and then a bend test or flexural measurement is done to find out what is the energy or what kind of energy or what kind of stress is required to extend this crack further. Okay. So, you have a existing crack which is created intentionally on the surface, and then you try to find out what is the energy required or the stress required to propagate it further. That is how that is the basic technique or the basic principle on which the fracture toughness is measured. So, with this basic principle there are different techniques, the different ways it can be realized this particular principle. So, two most common forms of test specimens with different configurations of the notch. So, the crack is actually created in the form of what we call a notch. Just a minute, there is a little bit of a I will make a correction, small correction here. Okay. So, there are two most common forms of test specimens with different configurations of the notch. So, as I have said, first of all we intentionally make a notch and then we keep the notch in such a way that they are under tensile load, and that will open up the crack and open up the notch, and the crack will try to propagate, and from the different stress required for to open to fracture the sample, one can measure what is the fracture toughness. There are two different types of notches which can be created. One is called the single edge notch beam test. In both the cases actually we are measuring a 4-point bend test or 4-point flexural test. Okay. One is the single edge notch beam, or in short ACNB test, and the other is chevron notch test, sometimes it is also called V notch test. Okay. So, these are shown schematically here. One is a simple notch has been created at the bottom surface of the beam, and then there is a 4-point bend test. These distances are S1 and S2 here, not in terms of L which we have used earlier, and then this is the B, the breadth, and this is the height. Okay. So, on the bottom surface we have intentionally created a notch, and that end of the notch obviously as small as possible, certainly of the order of less than around microns, some few microns, and this is a linear notch, whereas here it is a kind of BV kind of notch. Okay. So, there are two different configurations of the notch, and these two configurations give rise to two different formula to express or find out what is the value of the KIC, the fracture toughness. So, as per definition, the fracture toughness is basically the fracture or the stress or the energy which is required to propagate the crack. So, here it is S1 minus S2 A FF to BW square, where FF is the applied load for fracture to occur and A is a calibration factor. Okay. So, A is a calibration factor, and then this is FF is the load at which the fracture takes place, and B and W are the dimensions of the specimen. Okay. Whereas, in the chevron test or V notch test, the expressions are slightly different. A star, once again this is W square, it is 3/2, S1 S2 have their usual significance, and A star is the minimum value of a compliant function. Once here it is A is a constant, here also some kind of a constant. Okay. So, once you do the test and find out what is the fracture load or fracture stress, rest of it is basically a calculation. As you can always see that there are a lot of difficulty in getting accurate measurements, because they are quite sensitive to many different dimensions, many different ways of different parameters which we try to measure under this conditions. For example, the notch, how you are making the notch, what is the surface characteristics of that notch, where it is smooth, whether there is a some kind of serrations and all this, but three important parameters which one must always keep in mind, that is the sample dimensions may be too small compared to the stress zone ahead of the crack. Okay. So, in fact this should be sample dimensions should not be too small actually. Okay. If it is too small, then inconsistency will arise. So, that is what is says that possible reasons for inconsistency is that the sample dimension, what it means is basically the depth of the crack and then what is the rest of the material available for the crack to propagate. So, there must be sufficient material still available for the crack to propagate compared to the size or the dimensions of the crack in both the cases. The second important point to be noted is the internal stress generated during sample preparation, cutting, grinding, etc., is not fully removed before the measurement. Okay. As I have mentioned earlier, that any ceramic material being brittle, there is always a tendency or a possibility of generating different kind of internal stresses during its preparation, sample preparation, cutting, because samples have to be cut and ground, and annealing of these internal stresses is always difficult, because it is unlike in metals and alloys, just by heating one can remove the internal stress, because it is basically a dislocation movement. Here the internal stress generation removal is always difficult. So, one has to take special precautions, so that during cutting and grinding the additional stress are not generated, there is no stress concentration. So, things are very at its lowest energy level. Okay. So, this is another precaution one has to take, and the third precaution is the crack tip is not sharp enough. Okay. Well, it has to be sharp, at the same time it is not too sharp. Okay. So, there is again optimization required, how to generate a crack and how to generate the notch which you have created. So, if it is too sharp, naturally it will give a very low fracture toughness. If it is too blunt, it will give you a very high fracture toughness. So, there are standards available, of course, how to make these knots, and there are instruments available how to make such knots. Even for V knots, there are special instruments available to do that, but you have to operate those instruments properly, so that the right value is obtained. So, measurement itself is not a very easy task, but it is not impractical also. One can certainly realize these measurements. I am just giving you some principles. I do not have much time or sufficient time to discuss them in more details, but giving you some principles. There is another technique, measurement of fracture toughness by indentation cracking. Instead of creating a notch, one can initiate some cracks, one can generate some crack by indentation measurement. We have earlier see the hardness can be measured by indentation, and we have also mentioned that during hardness measurement there should not be any crack. The indents should be created under certain loads, in such loads, optimized loads, so there is no crack is generated. But if the load is more than that, then certainly the cracks will be generated, and that crack can be also used for fracture toughness measurement, because these cracks can be allowed to grow further under flexural strength or flexural load, and from that one can measure or one can make an estimate of the fracture toughness. So, these are the two ways of indentation followed by fracture. So, what is called indentation microfracture, another is called indentation strength bending method. Okay, indentation strength bending methods, right. We will discuss these things maybe in the next class. So, just to give you a broad outline, this is what we do in a indentation microfracture. That means, we do not fracture it, we allow the crack to grow, and from the crack length, you can find out what is the fracture toughness, under what load this fracture has been created, this cracks has been created beyond the indentation. So, you have a inlet forming, okay, that can be used, that has been used earlier for the hardness measurement, but if the load is more than that, then there will be cracks generated at the corners, because these are the stress concentration centers. So, the cracks will be generated, and there will be a particular way the cracks will be generated, and that from that you can find out what is the fracture toughness, right. So, here you are not allowing it to load, okay, load further. So, from the cracks by indentation itself, one can find out the fracture toughness, but there is another method by which one can see a indent is formed on the surface, and then it is allowed to fracture further under a bend test. Okay. So, the indent is on the bottom of this surface, and then the 4-point bend test is done, and from that also one can find out the fracture toughness, right. So, these are the two techniques. We will try to discuss little more about these things and maybe in the next class. Okay. So, we will continue our discussion on the measurement of fracture toughness by indentation cracking in the next class, and for the time being let me say goodbye. Thank you for your attention.